Hello, my name is Michael McHugh. I'm actually originally from Canada. I grew up in Southern Ontario, down in St. Catharines primarily. Moved to Portland about 4 years ago, and that's where I work now as a lead Python engineer at Urban Airship. Due to some recent events in the last week or so, I will be moving back to Canada quite soon. So, I'm going to talk to you about making noise and using that to generate terrain. So, for our purposes, we're going to be using a height map to represent the terrain. There's a few different ways you can represent terrain, but for our purposes, we're just going to use a height map. This is a pretty simple model. It works pretty well. You basically just have a two-dimensional array where each cell is the value at that XY coordinate. So like in here, the top most corner would be 71 meters high, and then the bottom one would be 19 with all those other ones in between. So this is how you generate a height map in Python. It's, like I said, pretty simple. You have your width and your height. You loop through both of them. And that should probably have said range width and range height, but we'll just pretend that width and height are actually just lists. And then you just call the value function and store that all in the map. And then you render it. And there you go. You've got a height map, and we're done. This is somewhere in the Midwest on my way here. I took a picture, and that's that. This is not actually what our height map is going to look like, but you can make things that look like this, just not in half an hour. So first we're going to talk about noise. When I say noise, most people obviously think about like sound and audio. That's not actually what we're talking about here. This is more like the noise, like in like an analog signal. They're not always perfectly smooth, so the noise is the bits that are wrong with a signal. So if you hear like signal to noise ratio, usually you're trying to get out all of the noise to get a clean signal, but we actually want the noise. The reason why is because, the slides did kind of chop off a bit, but that's fine. The reason why we want the noise is because it makes things look a lot more natural. If you don't have that noise, you're just kind of using straight lines, everything looks kind of manufactured and doesn't look real. Of course, all of our stuff is going to be manufactured, but we want to make it so that no one can know the difference. Luckily, though, because the way we're going to use it, we don't actually need to have a signal and then make it noisy. We're just going to use the noise, manipulate it in a couple different ways to make it basically work as if it was fine and the thing we wanted all along. That's primarily because if there's one thing I've learned about doing procedural content generation, which I've been doing for a while, you want to take shortcuts as often as you can, because it actually is quite a lot of processing power to do some of these things. So if you want to get anything in semi-real time, you take as many shortcuts as possible, and so one of those is just cutting out generating stuff. So the very simplest height map we can generate, that value function in the height map is just a simple height. We just return return the sum of x and y and put that into the height map, and this is what you get. It's not terribly interesting. All of the images here are actually, I built it in Python, and then it's forwarding out the height map to that little JavaScript thing that's rendering in 3JS. It's all going to be available online if you wanted to look at it. So that's what this is all going to be. So yeah, this is really boring. It's not really very interesting, but we can go and take a look at this, and you see this is just using completely random for every x and y, just randomly choose a number, and then use that as the height. It's also not very interesting. Still pretty boring to me because it's just a bunch of randomness and there's no like continuation between any of it. So we have these two things which are both very simple. Neither of them look very realistic, but both of them kind of have aspects that we want to get at. What we want is our random changes to happen, but we want those to be gradual. because if those gradual changes happen, it looks more realistic. Basically, for any 2 points that are close to each other, the difference in height should be pretty small, so it's a smooth change. But for any like arbitrarily large change in the height map on the x-coordinate, it should be an arbitrarily random difference. So this slide, it was the last slide I made. I agonized it over it for a while because I could never figure out a way to represent it well on a slide. But that's what I was just talking about here. So a sine wave, it has all the properties that we actually wanted. Because you see like the red lines there, with a small change in the x, it's a pretty small change, and every x is going to have a pretty consistent change in the y. But with the blue lines there, you see they all start at the same point, but depending on how far they are in the x, it's a completely different number, change in the y. So the first one's a large -1, the second one is a pretty small change, and then the other one is a pretty large positive change. However, this is what a height map would look like if you rendered it as a sine wave. Again, not very noisy, not very interesting, maybe a little bit more interesting than the previous 2 examples we had, but still not very interesting and not very realistic looking. Luckily for us, if you take multiple sine waves together, multiple sine waves have different phase shifts, so basically they start at a little bit different and have different frequencies. You can add those up and it actually looks noisy enough, so that's what we're going to do for now. So there's 3 different things we can change. One is the octaves. It's maybe a little bit confusing. I told you it had nothing to do with sound, and then these are sound terms because apparently computer people don't ever want you to make things easy. So it's hard to Google, but in this case, octaves is the number of waves you're going to be combining. The frequency is how fast it'll oscillate between high and low, and then the amplitude is just how much each different wave is going to affect the total output. So we're going to make some noise now using sine waves. This is how you generate those. You can have a list of parameters. Each of those parameters will determine how each sine wave is going to contribute to the final output. So we have the number of octaves for all of those you just go through. So you choose a random offset, so that everything doesn't line up perfectly and look kind of weird or not very natural. Then the frequency, what we're going to do is as the waves increase, as we get further and further in, we're going to make the frequency higher and higher. So that'll be noisier and noisier, but we're going to decrease the amplitude by dividing the amplitude by n+1, so that as the waves, or as the number of octaves go further, we're going to get smaller and smaller waves that fluctuate more and more frequently. So we'll have smaller details, but those details will add more noise to the situation. And then this is actually going to generate it. So we have these sine waves. Sine is a one-dimensional function. So you have one input, you get one output. Our height map that we're generating actually has 2 inputs, the x and the y, so we need to find some way to use the sine as a 2-dimensional thing. So what we're going to do is take the x, we're going to pass that into our sine wave using our parameters. You multiply the x by the frequency, so that's how you apply the frequency of the sine wave. And then you add that offset that we calculated, that random offset. You get that value out of there, and then we're going to feed that into the sine wave again using the y parameter, and this x parameter is the offset. So this way, as the x and y fluctuate, things will move together, but you're still going to get a good amount of randomness out of it. So this is just using the sine waves passed to that 3JS renderer I had. So the first one, the 1 octave, is just a single sine wave with the random phase offset. And so you can see it's basically just a sine wave in the x and the y. With the second one, you can start to see that there's kind of some perturbations that are smaller. That's the second octave coming in with the higher frequency and the lower amplitude. And by the third one, you can see it's actually fairly noisy, looks not too bad. But if you want to get more and more detail, you need to add more and more octaves. So if you wanted to get a larger height map for, say, a larger area, you need to have an even larger, or a larger number of octaves. And unfortunately, sine wave, though good as an example, because this process of taking inputs, running them through a coherent function like a sine wave, is how basically all the noise is generated. Sine is not great when you get to higher octaves, because even though you're doing that random offset, you have enough of them that you're actually going to start getting into similar harmonics. So they're all going to start lining up, and you can see there's kind of, this is 6 octaves and 8 octaves, and they both kind of have the same look, where there's kind of the X in the middle in the waves. You'll also kind of get an opposite one where the middle is down and then everything else is up. So that's unfortunate, but that's how noise is generated. Luckily, there's been a lot of research in this. Actually, quite a while ago it started, and we can just use theirs. So there are better equations and algorithms that have been generated. Ken Perlin in like 1985 generated this first one, which is classic Perlin noise. And that was used to generate textures for the film industry when they were first getting into CGI stuff. He actually won an Academy Award for this algorithm because of how much it was used in the film industry. But there were problems with it. And the primary main problem, it's hard to tell until someone points it out, and a little easier when you compare the two. But with classic Perlin noise, a lot of the features are aligned along the axes. So you can see there's a lot more straight lines, up and down and left and right lines that you can kind of see in those features compared to the second algorithm, which is simplex on the side, which looks a lot more random. Perlin noise functions similarly to what I just did with the sine waves, except instead of using a sine wave, they have a random vector at all of the integer boundaries. So then when you select a point, it will interpolate between all of those random vectors, and it kind of draws a spline between all of them. And then it does the same thing with the increased frequency and adds multiple different octaves together. So exactly the same way that we just did that with the sine wave, except instead of using a sine wave, it's random vectors and splines. Simplex noise was designed to fix the issues with Perlin noise, also designed by Ken Perlin. This was designed in like 2001. I can't really explain how this one works. I've read about it a bunch of times. I still don't really get it. There's like hexahedrons that they like squash and stretch and then unsquash, and then this comes out. I can explain more about Perlin, like classic Perlin noise afterwards, but go read the Wikipedia article on simplex, and if you can figure it out, please let me know. We actually won't be using either of those algorithms, though, because of the problems that we mentioned in Perlin noise, and because simplex noise is patented. It's patented for very specific use cases. I think it's only used if you're doing 2D texture generation, which we're not doing. So I think for most cases, most people are fine. But recently, I think in like 2014 or 2015, some guy randomly like made a blog post and posted on Reddit and was like, hey, I did this thing. It works basically the same as simplex noise, but it's a different algorithm. I'm calling it OpenSimplex. There's no patent. Have fun. So that's what we're using. Someone made a Python package that you can install from PyPI. You just pip install OpenSimplex and you get it. So that's what I did. And so yeah, this is what you get. OpenSimplex, and simplex noise as well, you just pass in a seed, and that's the only parameter you get. There are multiple dimensions. You can have 2D, 3D, 4D. I think that's the only thing the Python package supports, but in theory, the algorithm goes up to arbitrarily large numbers of dimensions. So we're just going to have this seed, which I use 1, 2, 3, 4, 5, and then you see it's again very simple. You just return whatever OpenSimplex returns, and then you get this, which I think is better than any of the things that I just built with the sine waves, and a lot easier to build for us. But The problem is that when we had the sine wave, we could mess with octaves and frequencies and things, which we can't do here because the only parameter we have is this seed. So instead of altering the equation with parameters, what you do is you can apply filters to the noise as it comes out. So there's a bunch of different ways you can do filters. This one here is just when every time you get the output, before you return it and render it in the height map, just raise it to a certain power. If you raise it to a power above 1, then what'll happen is it'll actually, because the OpenSimplex noise returns a number always between 0 and 1, or between -1 and 1, and I think I squished it and made it between 0 and 1. So then when you square it, what'll happen is the high points will move down a lot slower than the low points, because if you have 0.5 times 0.5, it goes down to a quarter, but like 0.99 to 0.99 is like 0.98. So the high points move down a lot slower than the low points. So as you can see, these ridges, or these noise, there's a lot more high points and low points there. Alternatively, if you use a root, so raising it to a fractional power, so raising it to a power between 0 and 1, what'll happen is all the low points will get pulled up and the high points will stay kind of the same. So you can see they kind of do different things. The raising it to a power will give you these peaks, whereas the raising it to or basically taking a root, like 1/4 in this case, will make it kind of more pillowy. Another option is you can use curves. So you can use cubic or a quintic, or you can just build your own. And this is basically a way to change the distribution of the output. So as you see here, basically, if your input is along the bottom, as your x between 0 and 1, your output is between 0 and 1. In this case, your input is going to stay very close to the bottom until halfway through, and then it's going to quickly jump up, and then it'll stay at the top. So what's going to happen is it's going to make a lot more valleys and a lot more peaks, but not a whole lot in between. So you can also just use a simple curve instead of doing a cubic or a quintic curve. So this is a very, very simple curve. Basically what it's going to do is it says any input value below 0.4, just treat that as 0. Any value greater than 0.6, treat that as 1. And then in between, we're going to linearly interpolate between them. And that's what you get here. So you can see areas of flat on the bottom, flat on the top, and then steep curves in between. So that's the first thing we're going to use. Then we're going to make another noise source. Sorry, I skipped a part. So what we're going to do is we're going to take, once you apply filters, another way you can change the output is by combining multiple sources of noise. So basically summing them together, or using one as a weight between two others, and that's what we're going to do. So the first one was going to be our curve. Then we've got this one where we're going to apply a couple filters to it. We're going to use that square root filter or fourth root filter to make it more pillowy, and these are kind of like our long or wide open rolling planes. So we will basically raise it to 1/4 and then apply a scalar filter to just drop it down so it's closer to the bottom. And then for mountains, we're going to use, we're basically just going to increase the frequency, similar to how we did it with the sine wave. If you multiply the input before you apply it, it'll make it more noisy because it'll move through that noise space a lot faster. And if you recall, the close things move slowly, far distances move more randomly. So by multiplying our inputs, we increase the frequency of the noise. So as we did here to get more bumpiness out of the mountains. And then we're just going to apply a multiplier filter on the end so that the mountains are higher than what we would get from elsewhere. And then we're going to combine all of those. Basically, we're going to take that curve filter and use that as the weight when we interpolate between the planes and the mountains. So anywhere the plane, that curve was 0, we're going to be 100% just using whatever the planes told us. Anywhere where that curve was 1, we're going to use 100% just whatever the mountains looks like. And in between those two, we're going to have a linear interpolation so that we don't get these crazy, sharp, jagged points. It's going to smoothly transition from planes into mountains. And that's what you get here. And that's Yeah, so that's basically what you do with simplex noise. You just take that, and from this point on, basically that's all you really need to know on how to generate terrain. There's a lot more things you can do. I didn't touch on coloring and texturing, which is obviously is all just gray. A very common way to do that is to just use the height value. So it's like anything below a certain point is blue because it's water, and then a little higher and it's like brown for beaches, and then green for grass, and then like white for snow tops on the top of mountains. So if you look online for like procedural generation, that's the typical kind of coloring you can see. You can use it for resource distribution, so you can say like, okay, if it's above like this point, like above when it's between 0 and 1, you say if it's greater than 0.95, then maybe there's some gold in these mountains. If it's below 0.1, then it's just rocks. So you can kind of use that to generate like the rules of your terrain. There's also, you can, if you have 3D, so this was all using 2D noise. You can use 3D noise where you have an X, Y, and a Z. It works exactly the same, except now you have another plane. So if you have your height map, you can then also have like a 3D noise where it takes the coordinate that you're in and generate noise, and you can use that to like generate cave systems by saying if it's below 0.5, then there's nothing there, and you can actually walk through it. If it's above 0.5, it's still solid. There's a bunch of other algorithms you can use to render. This was just using a height map rendering. You can use marching squares, which basically uses a density function and calculates whether or not you're inside or outside of a density, and then whether or not that's displayed. It's marching squares that has like 16 different options based on the squares. But I can talk about that afterwards if anyone's interested. There's a lot more interesting things, but there's not a lot of time. There's a lot you can do with this. This is just a Google image search for procedural content generation. Some of you probably recognize some of this. Some of you may have played some of this, and that's might be why you're here. But yeah, so there's all sorts of really, really interesting things. It's something I've been doing for a long time, never professionally. It's always been as a hobby, but I'd love to talk to people about it some more if there's any questions. Hopefully there's enough that I told you about this in this whirlwind tour that you feel like you can kind of try this yourself. I have all of the code that I use to generate those images are available on GitHub. So you can go and you can see the Python, you can see the JavaScript that rendered it, and you can just go mess around adding filters and trying different kinds of noise and see what you get. And that's that. Okay, cool. All right, I thought I was a little further along than I was, but there's time for questions if anyone has them.
If anyone has questions, you can come up to this mic stand here.
Hi, that was great. Thanks. Ever thought about, once you've made a terrain, how to fill it with lakes and rivers?
Yes. So one way to do that is you basically can just set like a sea level. The easiest way to do it is set a sea level. You say, okay, anything below like 0.1 on the height map, just set it to 0.1 and make it water. So then there's a point there. Another option, which is kind of neat, is so once you've generated your terrain, you can then generate another map that's not involved in generating the height and say, this is actually my moisture map. So you can say, okay, you combine your height and the moisture, and you say, okay, in areas where there's a lot of moisture, then there's lakes. If there's not, then there's not a whole lot. You can combine that as well. And that's how you kind of generate biomes, is you have all these different features and combine them together.
Can you explain more about how you're able to visualize those maps you were making?
Sure. So 3JS is a JavaScript WebGL rendering library. I like it a lot. I've been doing graphics programming for a long time. 3JS is actually quite simple. So all that was 3JS has a plane geometry. So I said, give me a plane geometry with like 30 segments on the height and 30 segments on the width, and then I took the JSON. I sent to JavaScript through I had a little Flask server running, and it would send the JSON over of a list of all of the height, and it would just iterate over those, alter the Z value of the plane, and then re-render it. So I cheated.
In your talk, you showed us some of the greatest hits of procedural generation games that we maybe recognized. I was wondering if you had any secret faves to share.
Maybe. I mean, Minecraft. I never got into Minecraft for the playing the game and the building. I always just actually played the free beta version that you could play in a web browser. Because I didn't care about the game, but I loved they did a lot with different biomes, and the procedural content generation was really neat. So I just dig around and there's a waterfall in this cave under the ground. That's really neat. So that's what I would do for Minecraft. So they did quite a bit. And Elite Dangerous is a game that's very, very, very pretty. It's not a terribly fun game to play, or at least it wasn't when it came out. It's been a while. But it's really, really pretty. They did a lot of really neat things. They have an engine called Stellar Forge, where they actually generate an entire world, and they have entire universe, galaxy. They have the entire galaxy. They have all sorts of data about each of the different star systems and how those star systems and the different suns have the weights of the sun. So what elements were more likely to come out of the fusion of that sun? So that affected how the planets were generated. And then they also overlaid actual stats about the Milky Way galaxy. So they would have the procedural content generation that they would then alter with actual data. So that was really, really neat. Dwarf Fortress is pretty cool. They do the stuff I showed here was mostly for real-time stuff. Dwarf Fortress has a generational system, so it'll actually generate each things in steps, so it can do a lot more interesting things. But it's a limited set because you can't have an infinite world at that point. But they would they'd generate the terrain, and then they'd run weather on it to affect where the different watersheds would appear, and then they'd run history simulations, so they would alter where the forests were based on settlements cropping up and down. So they would run that. So they'd generate it, and then they'd run simulations on it, and then keep doing multiple waves. So that was pretty cool.
That's all the time we have for questions. Let's give Michael another round of applause.